project number 4, linear modeling. Let's go to your statistics projects file and go to the 4th sheet. And once again, we're working with our business executives data set. Now we need to create a few new variables here to facilitate our analysis. The first one is called age C, which is the age variable subtracting off the average. That way our new variable will be centered at 0. And C stands for corrected, age corrected. So we'll say equal, grab your age minus the average, and you can hit A, Control Shift arrow down, lock it. We don't want that range to move. Alright, we can center and use 1 decimal and drag it down. Alright, so we have positive and negative numbers here, and the average of age C will be 0. Positive numbers are values that are above the average for age. Negative numbers are numbers that are below the average for age. Okay, now Gen D, this we want to convert gender, a qualitative variable, into a quantitative variable, 1 and zeros, ones and zeros. D stands for dummy. Now I want to create this dummy such that the value for male will be 1 and female will be 0. So we'll say equal if, and then logical test that equals male, and 1 comma 0. So female will be our baseline category, and we'll have 0 for female and a 1 for male. Now make sure you don't put quotes around the 1 and 0. Alright, this is what we can call this a male dummy. Drag it down here. Okay, so we see that all the males have a 1 and the females have a 0. So this is a male dummy. Now, this is an interaction variable. When you see a star there, it just means multiply. So we simply multiply age C and Gen D. And you can use 1 decimal. Center it, drag it down. Alright. Now before we go to the next page, let's create a named range for salary. We'll only need 1 in this project, so Control Shift, using the label, arrow down, right click, define name, and we'll call it salary. And then we'll scope it to the final project linear modeling. Okay, good. We'll save what we're doing. Remember, if you make a mistake in your named range, you have to go to Formulas, Name Manager, and then you can look inside there and find the one and delete it. So here we see the complete set, and I can sort it by scope. Complete set of named ranges for our entire project. Looks like we've used salary 3 times, and we've got them scoped separately, so there will be no overlap. Alright. Now on the second page, we see there's some duplication, and that's because when we do our analysis later on, we'll need some of the columns next to each other. So in order for the columns that we need to be next to each other, I had to duplicate some of the variables. So what we want to do here for age C then is just do a cell reference. So say equal, and grab the age C, enter, center it, and let's make sure we go down far enough, and let's see what we want there. The last one I have is 0.5, but we need a 1.5, so you got to go all the way down to the where that next spanning header is. Great. Promotions, we can do the same thing. Say equal, grab the promotions, center that. Age C by promotions is, again, you can grab that. Now you have to multiply it. Age C star promotions. This is an interaction variable again. 1 decimal, center. Drag it down. And so forth. Gen D will be the same, do a cell reference. Now education D1 and education D2, these are dummies for education. Notice that we have 3 levels here, and the rule is that you need however many levels that you have, you need that many levels minus 1 set of dummy variables. So for gender we only had 2 levels, male and female, so we needed 1 dummy variable to represent that. For education there's 3 levels, so we need 2 dummy variables. Now I'm going to make my, let's completed gender here first. Now you notice those little green dots there. Those are Excel looks for inconsistencies as a warning that it might be an error. In this case it's not an error. We'll just go in there, say ignore error, and get rid of the green ones. Now go ahead and create your, I want associates to be my baseline category, so I'll need a bachelor's dummy and a master's dummy. Just like I had a male dummy up here, 1 for male, 0 otherwise. This will be 1 for bachelor's, 0 otherwise. 1 for master's, 0 otherwise. All right, go ahead and create those, and then create your, using an if statement now, and then go ahead and create the product, the interaction variables. Okay. Okay, here is the second page completed of the data. And recall that you can go to the statistics project solution file to check your answers to make sure that they're correct. All right, there are the 2 pages of data from the statistics project solution file. All right, now let's begin our analysis here. Our first linear model is salary by age, and you can go to the linear modeling from linear modeling sheet, or the slide from the notes, and get the descriptions that you'll need. We'll use those in a moment, but this is an explanation of what each of the models are. We're going to be doing 10 of them. Okay, so the first one is salary by age. So we'll need our data analysis tools. So go to data. You should see data analysis up in the right corner. If you don't, recall you have to go to file, options, add-ins, hit the go at the bottom, and then make sure that the analysis toolpack box is checked. As a matter of fact, we're going to be using the solver later on, so let's at this point click the solver add-in and hit OK. It's a very powerful tool. Alright, there's the solver. Okay, so go to A79 and we'll go to data analysis, and we want to go to regression analysis. They're in alphabetical order, so regression is right there. Hit OK. Now for all these models, our Y variable will be salary. That's the one I always list first after the number here. Salary, that's the Y. And then to the right of the by are all the X variables. Now in this case there's only 1. And excuse me, just remember that the X variables that you use have to be next to each other in your data set. This is only 1 here. Also remember that whenever we have age in the model, we're going to be using age C, and whenever there's gender, we're going to be using gen D, and whenever there's education in the model, you have to use both education D1 and D2. You never use D1 by itself or D2 by itself. So, okay, here we go. So we can use this is why we created our named range. We can put salary up there for the Y. Now up here at the X, we can grab the age C with the label. Okay, hit labels. We want output range once in a circle, then immediately in the open box, otherwise you're going to overwrite your input range. And click up here under A79. And now we need residuals only. The only box we need is residuals. Okay, and then hit OK. Great, and then immediately go to Home and hit Center. Center everything up, and then grab your very first number there, the multiple R, and scroll down, get all the data, right, and then make it 3 decimals. Good. So this is the form. We can hit the Print Preview button up here to get our dashed lines and see that we're right on the edge of the page there. All right. Now let's red and bold the R square, adjusted R square, and the standard error. This will be the same for every one of these models. Let's red and bold the sums of squares, and red and bold the coefficients. These are the betas. They're in order. Beta 0 is the first one. That's the intercept. Beta 1, and then if there are more variables, they'll be listed down here. And the coefficients, beta 2, beta 3, beta 4, and so forth, will be listed right beneath. Okay, let's save what we're doing. All right, now let's do reproduce some of the analysis that Excel's done here from fundamental principles. Put salary right here, and then actually over 1. And then we can put here variation, and then variance, and then standard dev right here, and then null model, full model, and then percent reduction. And let's left justify those. And then we can go ahead here, transfer this format over anywhere is appropriate. Go to the Format Painter and then grab all those 3. Excellent. Good. Now the variation in salary. Variation, remember, is the top of the variance. So it'd be the each of the salary values minus the predicted. And that is going to be sums of squares total. So this is the variation, each of the salaries actually minus the mean, because it's the null. When you have the null model, there are no predictors in the model. So you got the standard variation that we've worked with from the very beginning of class. It's the top of the variance. So that's what that is, and we got 3 decimals and centered. Good. And then the full model will be the sums of squares residual. So this is what's left over after you've included age in the model. So it's the actual salary value minus the predicted. Good. And the percent reduction, therefore, is going to be the null value, let's use parentheses, null value minus the full model value divided by the null value. And let's turn that into a percent with 1 decimal. Excellent. You see here that that's what R squared is. The 0.631 matches up with the 61.3%. So that is, we've reduced the variation from the null model, which has no predictors in it, to 63.1% by including age in the model. So you always want to add variables to eat up the variation. So to the extent that you do eat up variation, you'll get a higher R squared, and the higher that is, the better then. Okay, so let's go to the variance now. How do you convert a variation? Well, into a variance, you just divide by the degrees of freedom, and in the very base case, we divide by n minus 1, and that is going to always be listed here let's do it this way. Grab this, sorry, the total divided by its degrees of freedom. And there's 35 observations, so we've got 34 here for our n minus 1. And we get 72.104. And then for the full model, now we have to account for the fact that we've got one predictor. So it's n minus, the rule is n minus, n is the 35, n minus p, number of predictors, which is 1, minus 1, which is actually refers to the mean, which if you can think of when we did a 34, you've got 1 less than 35 because of the mean. Down here now you've got 2 less than 35 because 1 for the mean and 1 for the age variable in our model. So we're going to take this now, grab the sums of squares for the residual divided by its degrees of freedom, and this now is a variance, but so you can think of it sort of as a generalized variance. It's a linear modeling variance. This is the basic variance we worked with from the beginning of class. This is the new variance from our linear model, and again now the percent reduction for that is 62.0%, and that's exactly what adjusted R squared is. Now the standard deviation then is just simply the square root of the variance, and we can drag that down, and you see here that the full model standard deviation is actually called the standard error. So we can confirm that that's correct, and then we can take the percent reduction in that. That's not listed over here, but it's meaningful as well, and it's 38.3%. So we've reduced the variation by adding age to our model, 63.1%, which is the same as reducing the variance by 62%, and reducing the standard deviation by 38.3%. Okay, make sure you get this done right, because we're going to copy and paste this for all our models, and you don't want to be reproducing errors. Okay, let's save that. Actually, I prefer this down one, so I'm going to cut this here and then paste it right below. Oh, actually, we can just drag it down. Yeah. That way it's easier to remember that this lines up right here with that. Otherwise, if you put it in the wrong spot just by one, all the numbers will be off. So, all right. Now let's put our description in here. Each of the models, you want to describe the meaning, the interpretation, or put down the interpretation of the coefficients. And where you get that is you go to your linear modeling slides from the Applia website, and you'll see in here where the descriptions are and how to get calculate the results there. So the first part here is the estimated mean salary at the mean age is. So you just type in here the estimated mean salary at the mean age is colon. Now let's left justify this. See, it's centered now, that's why it doesn't show up. Left justify it, red and bold. And let's wait for a second on that, because we want to put another description in which is longer. I want to line up the results. And by the way, that's going to be, well, here's the second one. The estimated change in mean salary for every unit increase in age is, this will be the interpretation of the slope. This is the interpretation of the intercept. So we'll say the estimated change in mean salary for every unit increase in age is. All right, good. Left justify that. Red and bold it. Save what we're doing. So the estimated mean salary to mean age is, and that's going to be the intercept. Good. And the estimated change in mean salary for every unit increase in age is, that's the interpretation of the slope. All right, save what we're doing. Now let me show you a little trick. Remember this, the units here are thousands of dollars, so it would be nice if we could put a $K$ period after that. And the way you can do that is you can right click say Format Cells, go to Custom, and then up there it should already say 0.000. Put a space, capital K, $, period, and then hit Enter or OK. And you see there that we've got a format now, custom format. It'll save with your file. So anytime you are in this file, you'll have that custom format in there. But of course, we can use the Format Painter. We don't need to go back to Format Cells. Hit the Format Painter and pop that format down there. So great, now we have our units specified. All right, let's do some more analysis here. We'll reproduce some of the things that Excel has done and from fundamental principles so we can see where everything is coming from. So right here, let's write predicteds, errors, regression, total, and next to that we can say SSR, SSE, SST. Good, and we can use the Format Painter here to get these looking nice. Okay, save what we're doing. Spelled errors wrong. Again, you don't want to type in any errors the first time because you can copy and paste this down for all the different models, because we'll be doing a similar analysis for the other models. Okay, the predicteds. Now, Excel prints the predicteds for us, but where do they come from? Well, here's where they're coming from. They're coming from the coefficients here in combination with the data. So remember, the equation is beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so forth. We only have a beta 1 in this case, beta 0. We have a beta 1 and we only have 1x. So, but it works like this: equal, grab the beta 0, lock it with F4, plus beta 1, lock it with F4 times x1. So x1 is age C, but we're on the first observation, so we have to go up and grab the first age C. Right there. Do not lock it, because when we copy the formula, we want the coefficients to remain locked, but we do not want the actual data values to remain locked. All right, now you can get immediate confirmation that it works because Excel has printed it, has listed it so we can see it. All right, and they match up. Okay, this is the actual values of the line. So the errors then are the difference between the salary values and the line. Errors. How much difference there is between what we've predicted and what actually occurred. So this is going to be the very first salary value, and it's good to memorize what cell it's in, B4, minus the predicted value. Right there. So this is the residual or error. Excel calls it residual. I call it error because when we do our three-letter abbreviations over here, we don't want two R's, one for regression, one for residual, so I call it error. So matches up. Let's drag it down, make sure they all match up. Good, and they do. All right, now regression is the difference between the predicted value and the value that you can think of as being predicted without any variables in the model, which is just the mean of the salary. So the difference between the point, think of a two-dimensional graph, and with X salary on the y-axis, age on the x-axis. Errors are the difference between the salary values and the predicted salary values, the line. And the regression then would be the difference between the line and the mean of salary, or the flat line of salary. So we're just going to say then, grab the predicted minus and the flat line predicting salary with no predictors in the model is just the average of the salary. Mean salary, good. Now this does not show up. Excel doesn't print this one, but we'll get confirmation that it works in a moment when we do our sums of squares regression. Now the total, that doesn't show up either, but if you think about the extra piece that's being involved there, it's the distance between the actual point and then the flat line. So we go first from the point to the sloped line, and then from the sloped line down to the flat line. That's two pieces. The whole distance would be the salary value all the way down to the flat line. So this is equal to B4, that's your salary value, minus the average salary. That's the total variation. And or the total component. Again, that doesn't show up. But now, interesting thing is that if you, just like in a single point, the total distance is equal to the error plus the regression. You see that that's always the case here. It works when you square and sum them up as well. So the sums of squares regression plus the sums of squares error will equal the sums of squares total. Now, what I mean by that, I can take sums of squares regression, the first one squared plus the second one squared plus the third squared and so forth. That's the sums of squares regression. Fortunately, there's a function in Excel to do that called SUMSQ. And then we grab all the regression values, right click, and we can get immediate confirmation that that works, that we've done everything right if that number matches this one right here. And it does. So now let's do equal SUMSQ for the errors, right parentheses, and then SUMSQ for the total. And you can verify that the sums of squares regression plus the sums of squares error does equal the sums of squares total. And you see that that's what Excel has printed out up there. So our numbers match, and we've got it. We've got what we're looking for. Okay, one other thing to do on this model, we want to do a residuals plot. And this is a nice technique to verify if the assumptions of the model are correct. As we want constant variance in our errors, and this is a very good way to detect that. So let's go ahead, come down here in an open spot, say insert, and we're going to insert a scatter diagram. Alright, now let's cut it and place it right here across from the 26. And let's make that, go to Format, make it 2.91 by 3.71. Alright, yeah, put it right in there. Let's save what we're doing. Good. Now right click up in there, say select data, and we're going to, you can grab, you can use the labels, predicteds and the residuals. Oh, that's not right. Actually, you know what, let's move that away first. It's a little tough to see. With this version of Excel, you don't see what data is being selected. So we can move it over here first. Right click, say select data, and then grab with the labels. Give it a second. actually, I just remembered that you have to have the X before. That's right. We want predicteds on the y-axis and residuals on the x-axis or y-axis. So again, select data. Let's try it one more time. Grab that data and hit OK. Let's see what we've got here. Yeah, believe it or not, that's what we want. Now we can cut it, paste it on 26. All right. Now let's go up here. You can right click or go in, remember, stay away from the center. You don't want to move the inside. If you can avoid it, go on the right side, say use the paintbrush and go to the very last style. Good. Go to the plus, and we want axis titles, chart title, no data labels, no grid lines, no legend. So that's what we want right there. All right, we can get rid of those lines. Right click on the line, say Format Data Series, and go to the color, say no line. Good. All right, cancel out of there. Now, we want to center the points, and I've determined ahead of time what the dimensions of the axes should be, so that we can simply copy and paste the chart and change the source data, and then all the data will fit on all the charts. So we want to go from -15 to 15 over here. So you can double click it. Yeah, bring up the menu on the right. Go from -15 to 15 by 5. Close that. Let's go to tick marks. Put the major tick mark outside. And then go to number, and we don't need a point 000. And let's go to the color and make it black rather than blue. All right. Actually, one more thing, go to the text options, and under axis options, we want to make the horizontal axis crosses at, let's go -15. Yeah, that brings it down the bottom there. Okay, now double click the x-axis numbers, and we want to go from 65 to 100 by 5. And again, we want to put tick marks on there, major tick mark type outside. And then go to number, and we want to get rid of all those decimals, which really crowd everything up. Very good. All right. Let's save it. The title should be Residuals Plot. And let's make sure that that's black and bold. And then down here on the x-axis, this is going to be bold and black. And we want to put in here salary predicteds. Up on the y-axis, bold and black. This is salary residuals or errors. All right, save it. Now let's right click on the points, say Format Data Series. Let's make sure they're the right size. go to the paint bucket there, marker, and it should be under marker options. Let's make them 7. Make them just a little bigger. Also, double click on the corner there. Let's add a border. Solid line, it should be black because we've been using black. All right, last piece, we want to put a line through 0. So we'll say format, actually that's not right, go back, close that, right click, say add trend line. So we want to say set intercept equals 0, push it forward 30 and backward 30. Good. Now go to the paint bucket and we want solid line. We want it black, but we only want it 1 point with a width. So this is under line, make it black, 1 point. There we go, save it. Good. Now we see here that the errors are roughly evenly distributed as you go from left to right. There's no funnel shape or any kind of patterns in it. There's an equal amount above and below the line. So we have what appears to be homoskedasticity. That means that the errors are the same as you move across from left to right for the predicteds. So that's a good looking residuals plot. And you can see any outliers if there were any, but they don't appear to be any. All right, that's the salary by age. Let's do the same thing for gender. I'll show you what can be, how much copying and pasting can be done. Okay, let's do model number 2, salary by gender. So we'll click here in A145, go to data, data analysis, regression. Again, we have salary up on our Y. It stayed there from the last time. Now, instead of age C, we want Gen D. Remember, anytime we work with gender, we're working with Gen D. All right, labels, change the output range. Goes right in A145 and hit OK. We have the residuals box checked. All right, home, immediately hit center. And then we can grab our numbers and make 3 decimals. Good, bold and red. The R square, adjusted R square, and standard error. Bold and red the sums of squares. And bold and red the coefficients. Alright, now we can take our initial analysis right up here of the percent reduction in variation, variance, and standard deviation. Control C. And line it up right there. Control V. Good, and you see all the formulas are transferred into proper slots, and we get, there's the R squared, the adjusted R squared, and the standard error, and the percent reduction in the standard deviation. Very good. Now let's interpret our coefficients down here, and we can go to our linear modeling slides. Here's model 2, and the interpretation is the estimated mean salary is, and then we have for females it'll be beta 0, and for males it'll be beta 0 plus beta 1. So we can come down here and say the estimated mean salary is, again, left justify that, and bold and red it, and we can say female and male, and left justify that, bold and red. And then this is going to be beta 0, so that's the intercept. And this is going to be equal to beta 0 plus beta 1. So beta 1 is actually the difference then between the males and the females. Let's go ahead and get our format right here. Say format painter. And change the formats for each of those. Okay, and we can go up, then grab this row of information. Grab these three. Control C. Control V. Alright, the predicteds, again, beta 0 plus beta 1 times x1 plus beta 2 times x2 and so forth. So it's beta 0, lock it, plus beta 1, lock it, times the first gen D from above. Good, and do not lock that. Does it match? Yes, it does. Go all the way down. Good, they all match. Yeah, errors, remember that's the salary value minus the predicted. So that was from B4, that's my very first salary at the top, minus the predicted. Good, that matches. So this person's salary is $11,938 below the predicted. Regression then is going to equal to be the difference between the line and the flat line. The flat line is the average salary, which is what you'd predict if there are no variables in the model, minus average salary. Again, this one does not, Excel doesn't print this one, so we'll have to wait for confirmation that we got it right. And then this one is equal to the actual salary value minus the predicted when there's no variable in the model, which is just the average salary. Alright. Now we can actually copy the sums of squares. Right? Control C. Control V. Excellent. So 1151, 1299, 124. Perfect. All right. Last thing we want to do is right click, copy, paste it again across from 26 right here, and then right click, say select data. Now that shows us our old one, remember? Or recall, or notice, and then we can use the labels for the new data and make sure we line it up right. It's, yeah, that should do it. Hit OK. And looks great. Right, now there's only two, looks a little odd, but there are only two predicted values, one for the female, one for the male. And we see then that the errors or residuals are roughly spread out the same above and below the line for both the females and the males. Okay, save it. Now in this next section here, we're going to make an important connection between the linear modeling and hypothesis testing that we did in the last project. Okay, recall that the beta 1 is actually the difference between the male and female salary. And we can test, and this t statistic here actually tests the null hypothesis that the beta 1 is equal to 0. In other words, we can test whether this is just random fluctuations in the data or if it represents something significant. That is, do the males are the difference between the male and female salaries significant or not, or based on what we see with this 11.516. Here's our t-statistic, and we can see the p-value is less than 0.05, which is your typical alpha. So we reject the null hypothesis that the male salary is equal to the female salary. Now, that should remind you of the two population hypothesis test that we did in the last project. And the question is, though, is it equal variances or unequal variances? And in fact, when you do a linear model like this with a dummy variable representing two groups, males and females in this case, it's a t-test assuming equal variances. So let's go to data, data analysis, go down, hit t-test assuming equal variances. And actually, before we do that, I forgot we need to get our data in columns, right? So the easiest way to do that is to come up, grab all your data. I grab it all because when you we're going to sort the data, and when you go back and resort it, you have to make sure you resort the same columns that you sorted. So so that I don't forget which columns, if I choose a particular subset, I just grab them all. So here we sort by gender, and now I have the female salaries right there next to each other, so I can right click, copy. Go down here, right click, paste. Good, let's go get the male values. Right click, copy. Paste. Good, and let's go up and resort our data. So grab all the data that you selected before, go to sort, and this time sort by executive. Get it back to where it was originally. Save. Good. Now we can run our t-test. Go to data, data analysis, t-test assuming equal variances. And male will be the first one. And then go in here, variable 2 is female. Now, a linear model assumes that the hypothesized mean, or uses a hypothesized mean difference of 0, always. So it's always an equal variances situation, and the hypothesized mean difference between the male and female salary is 0. So we're just testing input labels. We're just testing to see if there's any difference at all. And then click right there, and we hit OK. And there it is. Let's center these numbers and use 3 decimals. Good. We can green and bold the hypothesized mean difference, and red and bold the t-statistic. So green and bold hypothesized mean difference, red and bold the t-stat. Now look up here. See the t-stat 5.409 exactly matches the 5.409 up here. So you can get immediate confirmation that you did it correctly by checking the t-stat. And the p-value, so 5.524 times 10 to the minus 6 should be exactly equal to the p-value right here. Yep, 5.524 times 10 to the minus 6. Perfect. So it's exactly the same test. And what's the conclusion? We reject the hypothesis of equal means at 5%, because of course the p-value is less than 5%. So we can red and bold this one. Good, that's our conclusion. Wonderful. So you see that the hypothesis test, t-test, two groups, equal variances that we did last project is identical, equivalent to a linear model with a dummy variable in it representing two groups. There's actually a third way to do a hypothesis test, and that is with what's called an ANOVA. Now ANOVA is like a t-test, but it uses an F statistic, and it works for 2 or more groups. So the t-test is limited to only 2 groups, but the ANOVA is not, and it works for 2 or more groups. So in this case, we have 2 groups, so the ANOVA should give us the exact same result. So let's go up here to data, data analysis, and then all the way up here to ANOVA single factor, hit OK. Now the data is only one box for data entry, so we can grab with the labels all the data, even though there's not an equal number. Labels in the first row, and then we'll hit 227, hit OK. Excellent. Immediately hit center and grab the numbers right here, use 3 decimals. All right, now bold and red the F statistic. Now look at this F statistic here. This is testing the null hypothesis that the mean salary for the males and females are equal. The 29 exactly matches the 29 right up here, 29.252. Now, this is not a t-test, and the p-value, look, is the same p-value, 5.524 times 10 to the minus 6, and that same thing over here. So, in this case, when you've got 2 groups, the ANOVA F statistic equals actually the t statistic squared. See the 5.49, you square that, you get 29. We can prove it right here. Say equal, grab that, square it, and we see we get the exact same thing. So even though it's an F test, it's equivalent to the t test, because when you have 2 groups like this, the F statistic equals the t statistic squared. All right, good. Now let's put the conclusion in here. We say that's actually exactly the same thing. We can just copy it. Control C, Control V. All right, go ahead and do education model and the rest of them. Remember that you can go over to your linear modeling slide from the Applia website and see how it looks. See how the layout is here, the estimated mean salary, so forth. And there's number 4, number 5, 6, 7, 8, 9, 10. And let me show you a little bit about how I want this to look. Okay, here's the salary by education model, and you see how it's laid out there. The estimated mean salary is. You've got associates, bachelors, and masters. Now, you can do an ANOVA, the equivalent 3 populated. There's no t-test because t-test only works for 2 groups. There's an ANOVA here. You can do an ANOVA though, because that works for 2 or more groups. Now you're going to have to sort your data and get the data values from the top, put them in the columns like this, and then run your ANOVA. And note that the ANOVA right here, the F statistic matches the F statistic from the linear model. Now it doesn't equal, there's no single t down here to do the same testing, so this F doesn't equal any of these t statistics squared. But the F statistic, like it did up here for the model number 2, that F statistic did indeed match the F statistic from the regression, as well as the t statistic squared. Okay, so you'll verify that and put the conclusion there. Again, since the p-value is less than alpha, we reject the null hypothesis that the means for the associates, bachelors, and masters, the mean salary, are equal. So there's differences between those 3 groups somewhere. Now here's the promotions model. This is what you're going to write in there. And this is the model number 5. This salary, this has two variables in it now, age and gender. And this is how it's going to look for model 6 with the interaction. Then for model 7, it's a little odd, but I made the font a little smaller. Instead of 11, I made it down to 10 so that it would fit in here. And so I've got a cell reference there, put a plus, another cell reference here, and then I put star promotions. See, that's consistent with the what I've got here in the slides. All right, here's for 7, right? And then finally, or not finally, but the next one, this has got, again, reduced the font here so they can all fit. And then for model 9, when you've got age and gender, or sorry, education, gender and education, you've got a little simple layout like this, which is going to match the layout for number 10. Great, and recall that you can go to your solutions, statistics project solution file to see and all the correct results and make sure your numbers match up and the format matches up and so forth. So here it all the way down, 8, 9, and 10. Okay, to finish up this project, we're going to work with some new type of data, time series data, and we're going to do a couple of smoothing techniques and then a forecasting technique. Okay, this is time series data because there's only actually one study unit, let's say some business, and we're measuring sales for 12 weeks. Now, what's different about time series data is that that the observations are correlated. Right? You'd expect that week 1 sales is somehow related to week 2 and week 3 and week 4 and so forth. But there's usually a lot of noise, random noise in data, all sorts of data, including time series data. So you may want to try to come up with some kind of smooth line to represent the data, to somehow see what's happening behind the noise. So these next 2 techniques are good for that, smoothing. So this is called a moving average, and it's based on exactly what it says. You're going to calculate an average, so we can do this together here. Grab these 3. We're going to use an interval of 3, not 4. Good. So in the 4th week, we're going to compute a forecast, which represents the average of the prior 3 weeks. Okay, so we can center this. We can put 3 decimals. And then now, if we drag it down, see what happens. We get rid of that green dot, the green little thing there. We can see that the average moves because in Excel, with a relative cell reference, when you copy a formula, the range will move with it. And so you see there what's going on. Each new forecast is a different average, or an average of 3 different values. And now we can calculate a squared error to see how much, or what the difference is between the actual sales and the forecast. So we'll say error, sales minus forecast, and squared. Good. Center and 3 decimals. Drag it down. And then we can calculate the average to measure how, in a single number, to measure how much error there is. We can just calculate the average of that. It's called the mean squared error. These are the squared errors. So the mean squared error then would just be the average. And we can grab this. Oh, too many. Right click. Good. Center it. And let's red and bold it. So this is a single number that represents how much error there is. Save what we're doing. Now let's chart this. So go over here, and now this is going to be a new type of chart. We've used obviously the column, the pie, and the scatter. The scatter looks at 2 variables at one time. The column was just looking at 1 variable. Now if we do a line chart, again, it goes back to just looking at one variable at a time, but it's really good for time series data like this because the x-axis will be the values in order, and that can be our weeks 1 through 12, and on the y-axis we'll get these sales. So let's actually do the forecast and the sales. So we're going to right click. Actually, let's move this up, or down a little bit, and let's go to format and change the size from 3.13 to 4.5. All right, and slide it in there real tight so it doesn't slip over on the other page. Okay, save what we're doing. Good. We'll right click, say select data. Let's use the custom entry, say add, and the series name, let's call it actual, and we're going to plot the actual sales, right? Hit OK. Good. And then add another one, we'll call it forecast. And grab the same columns even though there's or same rows even though there's some missings in there. Excellent. And hit OK. Now let's change this, go to the paintbrush and use the very last style again. Go to the plus. We want axis titles. Put a chart title on there. Don't want data labels. Don't want grid lines. Let's put a legend in this time, and let's put it at the bottom. All right, good. Save what we're doing. Good. Let's change the axes over here from 14 to 24 by 2. Double click it. So we go 14 to 24 by 2. Good. And we can go to tick marks. Go major tick mark type outside. And go to the paint bucket and solid line black. That's good. Just make sure it's black. Yeah, it's black. Good. Now on the x-axis, double click those and go to line. We'll say solid line. It's black. Good. And go to the, yeah, we want tick marks, major tick marks outside, and labels, label position, no, that's fine. Axis options, yeah, we want axis position on the tick marks. See how the tick marks are in between the numbers right now? We want the tick marks on the numbers, or right next to the numbers. Good. All right, looking very good. Let's change our chart title. This is going to be weekly sales, and let's make sure that that's black and bold. And then over here, this title is sales, and make sure that's black and bold. And then down here for this axis title, should be week. And make it black and bold. And one final touch, let's put a border on the chart. Solid line, it should be black, right? Because we've been using black. Good, there it is. So see how the blue line represents the actual sales, and then there's quite a bit of fluctuation in there. And then the the forecasted value is more smooth than that, and sort of goes in between the extremes. All right. Of course, there is no forecast for the first 3 periods because we needed those periods to get the forecast for period 4. All right, that's moving average. Let's do the exponential smoothing. We're going to add a little twist to it. We're going to optimize the alpha. Exponential smoothing involves alpha, a chosen alpha, but we're going to let the computer choose the alpha for us to minimize the mean squared error. So how does this technique work? Well, we start with, in period 2, the forecast is the week sales value, week 1 sales value. So let's center that and use 3 decimals. Good. And then this now is a weighted average, and the weight is the alpha that we're going to choose. Let's put it down here. This is alpha and equals, actually I'll put this over here, center it, and then we'll start with 0.500 and use 3 decimals and make it green and bold. This is the flexible value. Alright, save what we're doing. Now this is the weighted average, and the weight is determined by alpha, so we'll say equal, it's going to be alpha, lock the alpha, times the prior week's sales, plus parentheses 1 minus alpha, lock that, parentheses, times the prior week forecast. Okay, good. So it's alpha times the prior week's sales plus 1 minus alpha times the prior week forecast. Good, and center that, 3 decimals, and drag this down. Good. Now what's our squared error? Again, is equal to, parentheses, the actual sales minus the forecast squared. Center that in 3. And then we can say in here MSE equals, and take an average. Alright, we get 10.669, which right now is larger than the squared error, mean squared error from above. Now let's copy this down. Copy, paste, slide it in there. Alright, let's change our source data. Right click, say select data. Now the actual, edit that. This is going to be the new values down below. Actually the same values, but in a different spot. And then a forecast. Keep the same label. And notice there's only one missing value for the forecast in this one. All right. Now with the weight being 0.5, it's basically just an average, a straight average of the two prior, the sales in the prior week and the forecast in the prior week. Let's now figure out what the alpha, or find an alpha such that we minimize the mean squared error. Right? Let's try, and there's a really nice tool to do that. This is the solver. This is the tool we added earlier in the video. Remember, you got to go to File, Options, same place where to the add-ins where the data analysis was, but we checked this solver box. So right now, let's open up the solver box. So hit the solver button. Now, we want to set the objective. That's the MSE, so make sure that that's selected. We want to minimize, so click the minimize button, and make sure then you check the alpha. And everything else you can keep the same. Well, it should say GRG nonlinear, and you can keep the box checked there, make unconstrained variables non-negative. All right, so that is the MSE box, the red one. This is the green one you want to minimize. So Excel is going to search through all the values for alpha such that, and find the one, choose the one that makes MSE as small as possible. And watch this. Bam, look what it did. That line, smooth, it's really smoothly fit through there. The alpha is 0.174 and the MSE went all the way down to 8.960. So it's a very powerful tool, the solver. All right, let's do the last one now. This is called a multiplicative model, and we're going to apply it for trend and seasonal aspects of the data. This also works if you have a cyclical component in addition to seasonal. That covers all the basic components, trend, seasonal, and cyclical. We're only going to work with trend and seasonal. The first step is to compute a moving average starting with quarter 4. By the way, this data is, you can think of it as swimsuit data for 16 quarters. You can think of this as fall, winter, spring, summer. Notice how the fall values and winter values are low, which makes sense for swimsuit sales. Spring and summer are high, summer being the peak. Fall, winter, spring, summer. Peak again. It starts to rise in spring and peaks in summer. Then it drops down, fall, perhaps not as much as spring, or fall, not as much as winter because of maybe sales and so forth. Fall, winter, no, there's spring, summer, fall, winter, spring, summer. Okay, so we definitely see we have some seasonal aspects to this data, and it looks like also every year the values are moving higher. So we have some trend aspect as well. Okay, so we need to pull, this technique is very clever. It pulls out the seasonal and the trend, or seasonal component, and then looks at the trend alone and then puts back in the seasonal factor in the forecast. So what we do here is we say equal, doing moving average for this whole year here, right parentheses. Good, and let's center it and use 3 decimals. And drag it down. All right. And we can get rid of the green dots. There's no error there. Now, if you think about it, this average represents sort of the middle right here between quarter 2 and 3. Right? This next one, after that, represents sort of the middle between 3 and 4. So if we want to bring back, or actually adjust these two here, if we take the average of those, we can actually get something that represents the year around quarter 3, right? So the center of 2 and 3 averaged with the center of 3 and 4 gives you 3. So this is called the centered moving average. So we take an average here then of these two, just 2 at a time, and center that, make sure it's 3 decimals. Yeah, it's number. Now this can only be taken to right there, because if you took it one more you would not have proper averaging, right? So we stop right here. Now this centered moving average, we'd like to know how much above or below the quarter that this represents. So if it's below, well, we can take just the ratio here, and we can see then that center and use 3 decimals. by taking the ratio of the actual sales and the centered moving average, we get a number greater than 1 if our sales is sort of high season, a number less than 1 if it's low season or below the average, right? So we see this is spring, summer, fall, winter, spring, summer, fall, winter, spring, summer, fall, winter. And it's making sense. These are numbers above 1 for spring and summer and below 1 for fall and winter. Now what we can do is combine. Notice how these are different. Here, this is spring, this is a spring, this is a spring. They're different, although they're of the same sort of rough magnitude above 1. So what we can do is average those values and come up with one set of indexes for all the seasons. So this is for fall. So what we want to do is take all the fall values. This is the first fall. Let's average these now. So here's the first fall. Lock it. And then lock this fall. And then there's one more fall right there. Lock that. Okay, center it. Yeah, make sure it's getting the right ones. Now we can drag this down. Keeps the same formula, but we want to move these values to the winter now. So these are all the winters. Good, 0.838, and drag it down again to save us some typing. But now we want to make sure that they're all lined up with the spring. Nope, that's not right. Spring will be there, and another spring will be there. Right, so fall, winter, spring, summer, fall, winter, spring, summer, fall, winter, spring. Good. And then finally, we move that ahead 1. Move these boxes 1 up like this. Good. So this is all the summer values. So fall, and so this represents the one set of seasonal indexes based on all the information. So we can copy this and paste it for each period, each year, and then actually we can use this for our prediction, the basis for our predictions. Okay, save what we're doing. All right, now what we can do here is strip off or remove the seasonal aspect from the sales. So we grab our sales divided by the seasonal index. Again, use 3. So this will be what's left over after we remove any seasonal aspect. In other words, see, dividing by something less than 1 will boost up the low season values, and dividing by something greater than 1 will minimize or shrink the high season values. So what's left over then, we can't go all the way, we can only go to here. What's left over is just any trend aspect. Good, save it. So now we can use a linear regression on the trend and then add back the seasonal. And you can do it this way. You can say equal we use the forecast function. Now the x will be the quarter, right? Now the known y's are the deseasonalized values, and we want to lock it with an F4. Known x's are all the x's here, 16 of them. Lock that. So this would give us a trend, a prediction based only on the trend. Now if we multiply back by the seasonal index, and don't lock that, well, we can put back the seasonal aspect to it. Good, so and center, and drag this all the way down, and this gives us a forecast. Good, all the way to 9.195, And then we can do a squared error again to see how close. Take the sales minus the forecast, square it, center, and 3. Now we can't go all the way, we got to stop here, and we can say MSE equals, and this will be the average, left parentheses of the squared errors, right to there, right parentheses, center, make it red and bold, and then center this one. Hey, there it is. Pretty small mean squared error. Let's look at a picture now and see what that looks like. So we'll say insert do a line chart again. Not a scatter. We're only looking at one variable at a time. Let's put it right here. Actually 2 lines, but only one variable. The x-axis will just be 1 through whatever. In this case, it's going to be 1 through 20 for our quarters. So let's go up here and let's make it, change the size of it. So go format and let's go 3.74 by 5.56. All right, and we can right click, say select data. Let's use the custom entry method. We'll say add, and this will be actual, and the series values. First one will be sales, and let's go all the way through 20. And then we can add, say, forecast. Get rid of that little thing in there. This will be all 20 of them. And then finally we can put the deseasonalized in there just to see what that looks like. That's the part, the prediction without the seasonal aspect in it. And that'll be these right here. Again, we want to choose all 20. Hit OK. All right, so Format Painter. Use the last one. Hit a plus. We want axis title, chart titles. Get rid of the grid lines. We want the legend. We want a legend at the bottom. Good. Chart title. We're going to say quarterly sales. And make it bold and black. Down here, this is quarter. Make it bold and black. And then I don't think it's black. Yeah. And over here, this is sales. Make it bold and black. All right, let's go from 4 to 9. By 1. Good. Then the axis, let's go to number. Get rid of the decimal, 0. And then go to tick marks. Say major tick mark type outside. Go to the paint bucket, make it, go to line, make it black. I think it already is black. Yeah. Good. And then down here, we can double click there, say line, solid line, black, and then options, tick marks, outside, axis options, axis position on the tick marks. Good. Alright, we can put a border on the outside. Excellent, there we have it. We can see how close the actual and the forecast are, the blue and the red. Amazing, but obviously must have been made up data to get that good a fit, perhaps. And then you see that the trend, or the deseasonalized trend only, goes right through the center there. We indeed see that there's a positive trend to it, to the data. Excellent. So recall that you can go to your statistics project solution and see the final results. Right, and that completes project number 4.